In this separations video, I'm going to discuss more details about how you would actually integrate the multistage Rayleigh equation. Remember that the difficulty here is that xd is not a constant, and therefore I can't take it out of the integral or treat it as a constant when I'm performing this integration. Rather, xd is a function of xb, and the relationship is not immediately clear. One of the reasons why this relationship is not immediately clear is because the relationship also depends on what the reflux ratio and the number of stages are. It also depends on the equilibrium data too. Forgot to mention that, but the nature of the equilibrium data usually comes into play anyway. So given these three things, our only option is to evaluate this integral numerically. So numerical integration is really the only answer. And if you're unfamiliar with numerical integration, that's in contrast to, I guess, analytical integration, where you just perform this integral and then plug in the limits. So numerical integration, it's kind of a brute force method. This is like finding the area under the curve. So in your calculus classes, when you learned like the Riemann sum, for example, or the trapezoid rule or the midpoint rule, those were all methods of numerical integration. And there's going to be a couple of steps that we have to follow. So the first step is choosing several values of x sub d. Choosing several values of xd. And typically, they do not have to be between your bounds of integration. So not between xf and xb. In fact, if you choose xd's that are in those bounds, then you are not going to see the full value of the curve that you need. What you actually need is you need xb to end up landing between xf and xb. And it's actually better if you have a whole range. So when I say choose several values of xd, I typically start at 0.95 and I decrease by 0.05 every time. And you can also decrease by 0.1, just has to do with the degree of accuracy that you desire, right? So on and so forth until I get to, it depends on how it's going, but it depends on if I get to 0.5 or say, that's typically enough. Well, I'm not going to say that. It depends, right? And I'll show you what it depends on. So choose several values of xd, and it doesn't require that you have to know what xd average is. So remember that xd is different in general than xd average. All we're trying to do here, remember, is we're trying to plot this function 1 over xd minus xb as a function of xb such that we can calculate the area underneath. So when I'm choosing several values of xd, it doesn't matter at all if the values that I choose are in some range or not. So I always start with this type of range. Then next, if I assume that the reflux ratio is known, assuming R is known, then for each value of xd, remember, because xd is a point that's on the operating line, I start off plotting where xd intersects the 45-degree line. And then if I know that and I know R, then I know the slope. Plot the operating line for each xd. Okay, and then step 3 is assuming n is known. Then I can step the number of stages. Where again, you have to be careful to count the reboiler as a stage. +1 for the reboiler. Okay, and I'll just put parenthetically here. So since the entire column is above the feed, there is no feed, remember. The entire column, we say, is in the rectifying section. Is in the rectifying section. Only use the rectifying section operating line. There is only one operating line. Only one operating line. So no feed operating line, no stripping sections, therefore no stripping section operating line. The fourth step would then be to, after you step the appropriate number of stages, read the corresponding XB. for each xd. Corresponding xb for each xd. And finally, step number 5 is to plot 1 over xd minus xb, where you now know what both of these pairs are, versus xb, because xb is the variable that we are integrating over. And finally, I want to compute the value of the integral. Compute the value of the area under the curve from the bounds. Value of the area under the curve from xb is equal to xf to final xb. All right, so also I'm going to show you in the next class period, so whenever we get together next, how to do this in Excel, but I'm just going to do a quick tutorial here on OneNote. So let's say I've got some equilibrium data. So a generic alpha equals 3, for example. I like to make myself a table, which is even easier in Excel. So a table of XDs. So for XD is equal to 0.95, for example, it's going to be close up here. And let's say I have given R and given N. So let's say that I'm not going to give a value for R. I'm just going to say it is a line like so. And let's say I have N is equal to 4 stages. So I'm going to step 5 times because the reboiler counts. All right, so at XD, I'm going to start on my light blue line and step 5 times. So 1, 2, 3, 4, 5. And once again, all these lines should all be straight, and I have a difficult time doing that on my tablet. So this is my XB that corresponds to 0.95. Hard to say what exactly that is with just sketching it and no numbers, but let's, for sake of argument, say that this is 0.40. So I could then calculate 1 over xd minus xb. So that would be 1 over 0.45. And therefore, I now have a data point, right? On a separate plot, so I'm going to keep doing this for multiple values of xd. So for xd is equal to 0.90, do the same thing. So this plot is going to start getting a little bit crowded here, but my reflex ratio is the same. So the slope of this blue line is the same as the last time. And if I step 5 times now, so I'm just doing it visually so that the plot doesn't get too crowded, I might get that my xb now goes down a little bit. So let's say, just for sake of argument, it's 0.32. I don't know what it would actually be, but you can use your imagination here. So I'm going to keep going with this. So carry this all the way down until I get a very good range. Do the same thing with 1 over xd minus xb. The last step, this what the second value, of course, would be 1 over 0.90 minus 0.32, by the way. After I have my table of xb's and 1 over xd minus xb, I'm going to put this on a plot, 1 over xd minus xb as a function of xb. And I should get that the value of the plot is somewhat U-shaped. You'll see that if you actually go through and do this for a wide range. I'm going to want to integrate this from, again, my bounds are going to be xb, so final, or at the end of the run, and xf, or z. I told you I was going to keep switching those up, and I keep switching them up in my head, but hopefully that's not being too confusing. Or z. All right, and the last step is to calculate the value of this integral. So you can do this any way that you like. One way, popular method, is the midpoint rule, where again you slice this thing up into little rectangles, taking the value in the middle of each rectangle and calculating the area of all these rectangles. Simpson's rule is another way that you could do it, and I showed you how to do Simpson's rule last time. Trapezoidal rule is another one. So methods of numerical integration. Simpson's. So again, look back to last couple videos for that, a few videos ago, I mean. Simpson's rule, midpoint rule, or trapezoidal rule. And that's all you have it. So after you've gotten that, then the problem is solved. So you might have a question of, well, what is going to be unknown in this problem? And I'm going to leave that until an example problem coming up. But typically you would have one of xb or xd total unknown, but the three equations that you would need, once again, are going to be the multi-stage Rayleigh equation and the overall material balances for the complete system and for a component A overall material balance. And like I said, we'll get to a practice problem next time, and I'll show you how we would actually do this on Excel practically as well.